So what about division? We've done addition, subtraction, and multiplication of complex number. So division of complex numbers, say we have something like 7 minus 2i divided by 3 plus 4i. What the heck? How do you rationalize this idea of a complex division? Well, let's think of what we do, what we can. Let's think of some ideas here. If we had 2 over 4 as a fraction, we could multiply this by 1 and we end up with 2 over 4. So it's the same thing. But what I could do instead of 1 is I can multiply it by, say, a fraction. So I want to turn this thing in the denominator into something else. For example, 1. I could multiply the denominator by 1/4. Then 4 times 1 over 4 is 1. We'd have 1 in the denominator. Of course, if I do that in the denominator, I have to do it in the numerator. So it's like the same thing. I'm multiplying this by 1. I still end up with 2 over 4. Well, this, we can see, is 2 over 4 in the numerator now, and 4 over 4 in the denominator. And you can see that it doesn't really change things. 2 over 4 over 1 still equals 2 over 4. And you might think, well, this is kind of a circular approach. But this is the sort of approach we're going to use, and it's going to actually bear fruit for us in these complex numbers. So in order to do this, we're going to make a definition of something we call the complex conjugate. So if we have a complex number, a plus bi, the complex conjugate of that number is just a minus bi. So this is our complex conjugate. And why is this useful to us? Because we're going to do the same thing we did up here in the red balloon. And we're going to change our denominator because we're going to multiply this complex number by another complex number where the denominator here is the complex conjugate. So if the denominator, if we're multiplying by a number here in the denominator, we have to have the exact same number in the numerator up here. So this will be 1, and this won't change our original equation. But we'll see that when we operate in the numerator and the denominator, we're going to get some very beneficial results. And here we are. You can refer back to the multiplication to run through this. I've just put down the results here. When we multiply the numerator, we get 21 minus 28i minus 6i plus 8i squared. And when we multiply the denominator out, we get 9 plus 12i minus 12i minus 16i squared. And look what happens here. The 12i and the minus 12i cancel. So we lose our imaginary components now in our denominator, and we're going to have a denominator we can work with. And over here you might say, well, there's still an I over here, but this is an I squared, and we know this is going to turn into minus 1. So I can simplify these things. 21 So I have 21 minus 34i plus 8 times minus 1 up here. And I have 9 minus 16, and again, I squared turns into minus 1. So up in the numerator, we have 21 minus 8, because this is 8 times minus 1. 21 minus 8 is 13 as the real component, minus 34i. And in the bottom, we have 9 minus 16 times minus 1, and so 9 plus 16 is 25. And that is our result. We could rewrite it, I suppose. We could put this 13 over 25 here, minus 34 over 25i. If we wanted to, we could write it like that. But either one of those are acceptable solutions. Okay, so let's solve a word problem. So in alternating current circuit, the voltage E follows this relationship. Voltage equals current times impedance, where I is the current and Z is the impedance. Now, if we're given the voltage as this complex number and the impedance as this complex number, let's find I. Well, we see with some algebra that I equals E over Z, which means I is going to be 4.2 minus 3i over 5.3 plus 2.65i. So, looks like we have the division of a complex number. We can handle this because we can use the complex conjugate of the denominator, 5.3 minus 2.65i. And we know this will end up giving us something that is a real number in the denominator that we can use. But if we multiply the denominator by 5.3, we've got to do the same thing in the numerator. Otherwise, our equation is not the same anymore. Okay, multiplying the numerator together, we end up multiplying 4.2 times 5.3 is 22.62, 22.26. After this one, we get minus 11.13i, and then we do, oops, reverse that. We do 3i times 5.3, which is minus 15.9i, and then 3i times minus 2.652, which gives us minus 3i times minus times minus a positive 7.95i squared. And in the denominator, we get 5.3 squared, and then 2.65 times 5.3i minus 2.65 times 5.3i. So we end up with, and then finally we get these last two numbers squared, minus 2.65 squared, I squared. So this, because we use the complex conjugate, this is always going to happen. You're always going to get these two middle terms canceling out, and you're going to always result in a real number in your denominator. And in this case, our real number is 5.3 squared. And then I squared is minus 1, so minus 1 times this minus is going to turn this into a positive. So we still keep the coefficient, though, 2.65 squared. So this squared, this squared. In the top, we're going to end up with 22.26 minus 11.13 minus 15.9 is going to be minus 27.03 I. And then, of course, this is going to be plus 7.95. I squared is minus 1, so this is going to be minus 7.95. And for just a final iteration, let's go 22.26 minus 7.95 is 14.31, and then minus 27.03i. That's our numerator. Use these lines here since these are so long. And then our denominator, when we square these and add them together, we end up with 35.11. And now I can take the 35.11 and divide by each of these coefficients. So 14.31 divided by 35.11 is 0.408. and then I subtract off 27.03 divided by 35.11 is 0.77 I. And this is the amperage, amps. So this is our final answer. That's what the current is in terms of a complex number.